So we have considered the basic of the parametric approach and stochastic frontier analysis. So now let us have a look at this application of stochastic frontier analysis in this case of Finnish electricity distribution units that we have considered before in the context of DEA. So recall that we have a cost frontier model with single input, the total cost, and 3 output variables which define the cost frontier. In addition, we have a z variable that characterizes the operating environment of the firms, and we have the composite error term consisting of both inefficiency term u and noise term v. Notice that in the case of cost frontier, we assume that this inefficiency term u has a positive sign. To estimate this model by parametric methods, the usual approach is to postulate some specific parametric functional form for the cost frontier in advance. So in this slide, I have specified the Cobb-Douglas functional form, and I will later also consider the Translog briefly. So this is the key characteristic compared to the non-parametric axiomatic approaches that in SFA we always need to specify the functional form of the frontier in advance. Notice in this formulation that this right-hand side of the equation is completely linear in parameters. So there is this intercept alpha, slope coefficients beta, then there is a delta coefficient for the z variable, and a composite error term. So if we think about this impact of u and v together as a composite error term of a regression model, we can simply estimate this equation by linear regression by ordinary least squares. So this is what I have done here on this slide. So I've just applied ordinary least squares to this Cobb-Douglas functional form, and here is what we have. So firstly, notice that the R-squared statistic is very high, 0.98, indicating like almost perfect fit to the data. The reason for the very high coefficient of determination here is that there is very large differences in the size of the companies. Some companies are enormously large compared to the smallest one. So it's very, very easy to explain the variance in the total cost based on these variables. This doesn't mean that there are not any efficiency differences remaining, as we will see shortly. Then if we look at the parameters of the Cobb-Douglas function, firstly from the perspective of statistical significance, notice that the p-values are almost equal to 0 for all variables. So all of the coefficients are highly significant. Then if we look in more detail to the coefficients of the cost function part, this energy, length, and customers, notice that the logarithm of customers gets a negative sign. I have highlighted this by red color in the table. And this can be very, very, first of all, counterintuitive, but also problematic if we apply this kind of techniques for the incentive regulation, because a negative coefficient would give an incentive for the regulated companies to decrease this output. So there would be incentive for the distribution networks to try to get rid of customers, decrease the number of customers, or at least not connect new customers, even though they are obliged to do so. And it is kind of counterintuitive that as the number of customers decreases, the total cost would increase. I will get to this point shortly. Then if you look at the sum of these coefficients of the 3 output variables, so remember that in the Cobb-Douglas functional form, the sum of those beta coefficients yields the scale elasticity. So if we take the sum of this 0.57 and 0.52 and minus 0.14, in fact, the scale elasticity comes very close to value of 1, suggesting the constant returns to scale. So what if we then apply this very classical approach to efficiency analysis, corrected OLS? So on this slide, I have done this corrected OLS approach. And I first renormalized this regression residuals by subtracting the largest value of the residual in the sample. And then I take exponent function because we have the Cobb-Douglas functional form to get this kind of percentage value for the efficiency. So on this slide, I indicate for the sake of comparison the efficiency scores of the first 8 firms. So it's possible to compare to the DEA results. And you can see that even though the R-squared statistic was very close to 1, there are still considerable performance differences in this sample. So it would be wrong to conclude that if the R-squared is very close to 1, that there would be no efficiency differences left. In fact, there are quite substantial performance differences. The average COLS efficiency would be about 68%, with the standard deviation about 11%. So notice that when we compare this kind of deterministic frontier technique like COLS to the DEA, then these numbers are comparable to the DEA in the sense that both approaches would attribute all of these deviations just to the inefficiency. So this COLS doesn't now include any noise. And you see that the average efficiency score is considerably lower in the COLS approach, and this is because of the more restrictive functional form of the frontier. So imposing this Cobb-Douglas functional form decreases the efficiency compared to the DEA, which did not make any kind of parametric assumption about the functional form. What about this if we extend this Cobb-Douglas functional form to the Translog by including the second order terms? So I have done that one also, and this is the again with the ordinary least squares I have estimated the Translog functional form. In this case, the coefficient of determination R-squared statistic slightly increases. So remember it was 0.98, so we increase it to 0.99 with the Translog functional form. And now we have included, in addition to the logarithms of energy, length, and customers, we have also the squared values, and then we have the cross products. We can see from these results that there are 3 of the components have negative values. And it is not immediately clear from here that what is the output elasticity or sort of cost elasticity of outputs in the sense, or what is the returns to scale, because those depend on the values of the output variables now. And this, in my view, is also a limitation of the Translog functional form, because the results are not really so immediately, results do not have, or the coefficients do not have such a natural interpretation as in the case of the Cobb-Douglas functional form. It's more difficult to interpret those coefficients and to see, for example, is the negative value a problem or not. Of course, in the Translog, it's very difficult to ensure that properties such as monotonicity or convexity would generally hold. I will argue later in the course that actually, in fact, for sure, in the Translog functional form, either monotonicity or convexity have to be violated, at least in some point. So one issue, if we want to expand then to the stochastic frontier from the linear regression, is I noticed that in the case of the Translog functional form, the residuals are wrongly skewed. So if we calculate the skewness of the residuals, we get the value of minus 0.318. So we have negative skewness in the residuals, whereas in the cost frontier, we would expect that the skewness is positive. And this is a common practical issue in the stochastic frontier applications, because if you would now apply some stochastic frontier algorithm, then it would indicate immediately that there is some specification error for the wrong skewness. So in that sense, this kind of translog specification without some kind of additional data manipulations will not work for the SFA because of the wrong skewness. And this kind of problem actually can occur even if you have completely correctly specified model. So this is one of the limitations, that sometimes the residuals are wrongly skewed even in the correctly specified model. But from the practical point of view, if the regression residuals have negative skewness when the positive skewness is expected, then there's nothing that we can do. So therefore, in this example, I will return to the Cobb-Douglas functional form. In fact, if we would also apply statistical tests, like for example F-test to test for the restrictions, we will find that introducing these second-order parameters of the translog does not increase the fit significantly. And we can again recall that the R-squared statistic of the Cobb-Douglas functional form was already very high, 0.98. So there is not really significant increase in the empirical fit by introducing these second-order terms. And we also have this problem of wrong skewness. So let me then next consider the what can we get with the stochastic frontier analysis. So here are the results from the R tutorial prepared by Sheng Dai. So firstly, notice that we will get similar kind of regression output like in the case of the ordinary least squares. So you have the coefficients, standard errors, and also the p-values. And we will also get the mean efficiency in this case. So this is nice feature in some sense when in the stochastic frontier analysis. It's so closely related to the regression analysis, and I would argue that it's a good idea to start first with the linear regression techniques like just OLS to gain insight about the application. Also, it's good to look into issues like heteroscedasticity testing or multicollinearity. Of course, there are techniques in the SFA, but also it's possible to start first by the linear regression and then continue to the SFA setting. So what can we get then in addition with the SFA? So firstly, remember that the main idea in SFA is to decompose this composite error term consisting of inefficiency and noise to these two components. So this requires always some parametric assumptions. So here is, for example, for the case of normally distributed noise and half normal inefficiency, I have taken these equations from the classical article of Eigner, Lovell, and Schmidt that the variance of the composite error term, the sigma squared, is equal to the sum of the variances of the u and v terms. So sigma subscript u squared and sigma subscript v squared. And then we can also introduce parameter lambda. So this is not the intensity weight of DEA, but now here the lambda coefficient refers to the ratio of the standard deviation of inefficiency sigma u divided by standard deviation sigma v of the noise term. So in some sense we can think of the lambda parameter as the signal to noise ratio. And on the bottom part of this slide I have taken the results produced by R in this example. So we can look at, for example, here this firstly, if we think of this sigma squared u, sigma squared v, and total sigma, those are available. The sigma squared is this total variance of the composite error. It is on the first line, the rightmost element, and then we can verify that this is equal to the sum of sigma squared u and sigma squared v, which are indicated on the second line, second and third column. So if we take the sum of the sigma squared u and sigma squared v, we get to the sigma squared. Okay. This R code also produces the signal to noise ratio lambda. So lambda you can find on the third line and third column, value 0.229. And this is the ratio of the standard deviation. So notice that we can take standard deviation sigma u and the variance sigma squared u. And those are of course, just sigma u squared is just a squared value of sigma u. You can also verify that. So notice that the lambda coefficient is 0.229. So it's approximately 1/4. So that indicates that about 1/4 of the total variance is attributed to the inefficiency. So in about 23% of the variance of the noise term. Sorry. So the variance of the noise term is in this case is much larger, and we can essentially decompose the variance to this inefficiency term and noise term. So if we compare, for example, sigma u and sigma v, so sigma v is found as on the first column of the third line, 0.16, whereas sigma u, it is the rightmost column on the second line, is 0.037. So it's about indeed about 1/4. Sigma u is about 1/4 of the sigma v. So this suggests that there is much more noise than inefficiency in this sample. And this leads to this relatively high level of expected efficiency in this particular case. So this is needed to estimate the efficient cost frontier. If we then apply this John Rowe Lowell Matherow-Smith approach to get firm-specific efficiencies, we can do that, of course, in SFA. So here is an illustration how the results look like. I have reproduced here the first 60 observations just to illustrate that there's almost no difference in this SFA estimates using JLMS. So notice that almost all of the firms, according to this kind of classical SFA approach, yield about 0.97%, so 0.97, so 97% efficiency, and there's almost no difference whatsoever between the firms. This is in sharp contrast to this deterministic COLS results that I discussed earlier. There was large differences in performance according to the deterministic parametric method, as was with the deterministic DEA, but because this SFA approach attributes almost all of this, or very large proportion of the deviations to the noise term, then as a result, almost all of these firms are almost equally efficient. So if we believe that there is almost no difference in the efficiency across firms and that the efficiency is relatively high, then this is what the SFA produces. But these efficiency scores are very, very dramatically different from the deterministic techniques. Anyway, this illustrates that it is possible to use SFA to get firm specific efficiency scores, but in this example we find actually that almost all of the deviations from the frontier are due to the noise term, and there's very little inefficiency present according to this model. Then again, we come to the question: okay, is the model correctly specified? Can we rely on this kind of estimates? So we come back to that issue a little bit later. But to summarize the application of SFA in this particular example, as the main advantages of SFA, I would see the intimate connection to regression analysis. This makes it a very natural approach to anyone familiar with regression analysis, like econometricians and applied economists. And this also allows us to incorporate usual techniques from regression analysis. We can consider issues like heteroscedasticity and multicollinearity and potential autocorrelation and so on. So all of the toolbox of econometrics becomes immediately available for the applications of SFA. And like I mentioned, it is perhaps a good idea to start first with the linear regression analysis and to gain insight, and then use the SFA part as an add-on to decompose this composite error term later, because because anyway, implicitly this linear regression is underlying the SFA as well. And for example, if we had the wrong skewness of the residuals, then SFA just boils down to the linear regression. Also, the probabilistic modeling of inefficiency and noise are very useful features of the stochastic frontier analysis. We can readily test hypotheses, estimate confidence intervals, also for those parameters of the inefficiency distribution. So far, I have restricted attention to the cross-sectional setting here, but of course, the stochastic frontier approach easily extends to the panel data. We can utilize the panel data techniques like fixed effects and random effects, and also build up a parametric structure to the and some time trends to the panel data setting. So those are clear advantages of the stochastic frontier approach. There are also, in my view, several disadvantages in SFA. And firstly, of course, as we noted in this example, we need to have some parametric assumptions regarding the functional form of the frontier, but also for the inefficiency distribution, and also we need to heavily rely on the normality assumption of the noise term. And these assumptions are largely testable, of course, untestable. Of course, we can test between Cobb-Douglas and Translog, but we cannot really easily get rid of those, especially for the inefficiency distribution. There exists some kind of semi-parametric variants of stochastic frontier where we replace this functional form of the frontier by non-parametric specifications, and we will discuss that later. But in the classic SFA, the parametric assumptions can be extremely restrictive. We noticed in this empirical example that for the Cobb-Douglas functional form, we had violation of monotonicity because one of the coefficients was negative, and this can be very problematic in the regulation application. And unfortunately, it's also relatively difficult, virtually impossible, to impose some shape constraints. It's also well recognized in the context of the Translog functional form that imposing shape constraints can sacrifice the flexibility, so the biggest advantage of the Translog functional form. And we will also later pay attention to the modeling of multiple outputs. So I will argue that both Cobb-Douglas and Translog functional form are not suitable for the modeling of cost frontier, which has multiple outputs. It simply has the wrong curvature, but I come back to that issue later. And one thing that I did not really discuss so far, but if you think about flexible functional forms like Translog, remember that we have the first order parameters, but also then for the second order parameters, we need to take the squared values of the variables and their cross products. And there is a potential issue with the multicollinearity, especially when these output variables themselves are very highly correlated. So there is potentially the multicollinearity is causing the issue that we had this negative coefficient for one of the variables in the Cobb-Douglas specification, and using the Translog, the multicollinearity problem certainly doesn't get away, but gets even worse. So we will continue the discussion of SFA with the modeling of the Z variables with some alternative techniques, and I come also back to the panel data modeling a little bit later. But as the next step, we will go to the semi-non-parametric setting and consider the unified estimation of the frontier model with the so-called stochastic non-parametric envelopment of data, often abbreviated as STONE.